Our next speaker is coming from Italy. His name is Vincenzo Senatore. He's a PhD student at the environmental engineering at PhD student in environmental engineering at the SEED, the Sanitary Environmental Engineering Division of the University of Salerno. He holds a master's degree in civil and environmental engineering from the same university in Italy. He has been visiting researcher at IMDEA Energy in Madrid and Polytechnic University of Catalonia in Barcelona. So his main fields of expertise are the implementation of photobioreactor for carbon dioxide capture, pollutant removal, and valorization of microalgae. So Vincenzo, please.
Thank you. Hi, everybody. Today I'm going to talk about our last work that is entitled Advanced Photo-biotechnology for the Simultaneous Control of Volatile Organic Compounds and Greenhouse Gases Emissions. First of all, I would like to give you a briefly introduction about the sources of volatile organic compounds and the main effects. So the main sources of volatile organic compounds, as we know, coming from road and non-road transportation, energy production, distribution and use, paint, inks, glues, and other sectors such as the petrochemical one, and also from environmental protection plants. This type of compounds has also negative effects on the human health. As we know, volatile organic compounds, some of them are carcinogenic, teratogenic, or mutanogenic. They can cause also irritation, headaches, liver and kidney damage, and also photochemical pollution, and can cause other annoyances. As we know, we have two big families about air treatment technology, volatile organic compounds treatment technology, that are chemical physical technology and biotechnologies. The chemical physical technologies, as we know, works within a really high range of pollutant concentration, more about higher concentration, and also within a wide range of high flow rate. On the other hand, biotechnologies works within a lower pollutant concentration and within a medium range of air flow rate. So we know that physical chemical treatments are costly, mainly because they consume a lot of energy, but basically also a lot of chemicals. And as we know, there are a lot of ongoing study during the last 20, 30 years that are trying to develop to push natural-based solution, to use natural-based solution to degrade this type of pollutants. So the main goals of these studies are to develop and evaluate an integrated technology for the abatement of volatile organic compounds with a simultaneous capture of carbon dioxide, evaluate and maximize the efficiency of the proposed technology in terms of solvent abatement and carbon dioxide capture by using different nutrient sources such as urban wastewater and dairy wastewater, and assess the production of biomass to evaluate its potential in convert in energy to make the process more sustainable and more effective. These goals are also in line, as we know, the famous Sustainable Development Goals are in line with the seventh goals, that is renewable energy, and the 13th climate action. The research was conducted at the Sanitary Environmental Engineering Division in the University of Salerno, and that is located in the south of Italy. Here we can see basically our experimental setup that is composed of two reactors. One is a moving bed bioreactors, R1, that is inoculated with activated sludge, has a working volume of 6.5 liter, and is filled with 30% of plastic carriers, the one that we have in the moving bed bioreactor in wastewater treatment plants. The second reactors, R2, is an algal photobioreactors that is inoculated with microalgae, has a working volume of 26 liter, and it works with an illumination rate of a cycle of 12 hours light, 12 hours dark, and we use LED lights basically. The light intensity ranging between 6,000 up to 9,000 lux. Also, we can see here the gases feeding system that is composed by an air compressor and a syringe pump, in which is located a syringe that contain liquid solvent, pure liquid solvent, that are mixed in this mixed chamber. And also we can see 3 different gas sampling ports. That one is located in the inlets of the first reactor. The second one is located at the outlet of the first reactor, which is also the inlet of the second reactors. And the gas sampling port 3, that is at the outlet of the second reactors. So basically, in the first reactor, R1 was inoculated with activated bacteria. So we took activated sludge from a wastewater treatment plant that is located in the south of Italy, in Battipaglia. This sludge was centrifuged and was resuspended in a synthetic wastewater medium and then inoculated in the reactor. In the second reactor, R2, we use Chlorella vulgaris as a microalgae strain. We pre-cultivated this strain using a bowl mussel medium, and then we centrifuged this and resuspended in a synthetic wastewater medium, and that we use as an inoculum in the second reactor. Here we can see basically the experimental program and operating condition. We use there were 6 stages. Basically, the first 3 were the one in which we use synthetic urban wastewater as a nutrient source. The last 3 we use dairy wastewater as a nutrient source. Also, what changed during the overall experiment, we try to increase in each stage gradually the solvent inlet concentration, and we also increased during the last 2 stages the light intensity up to 9,000 lux. Here we have basically the analytical instrument and methods that we use to characterize the gaseous phase. So we we measure toluene concentration at the sampling port 1, 2, and 3. We did this measure daily, and we use a GC PID. Also, we measured the CO2 concentration at the sampling port 1, 2, and 3. We measure this concentration daily, and we use a GC TCD. Also, the pressure was monitoring daily with a pressure meter. Here we can see the parameter that we use to characterize the liquid phase of the 2 reactors. We measured the ammonium, the total suspended solid, chlorophyll A, dissolved organic carbon, and ions, nitrate, nitrate, sulfate, twice a week. And then we measure it daily, pH, dissolved oxygen, and temperature. Here I'm showing you some of the results that we obtained. Here we have the average removal efficiency and elimination capacity of toluene. We can see that the average elimination capacity expressed in terms of gram per cubic meter per day was, the range was around 90 to up to 131 gram per cubic meter per day. Which is like an average removal efficiency that range between 97 to up to 99%. Also, as we see, the inlet load is overlapped on the elimination capacity curve, because we were in the range of 90%, so it cannot be really distinguished. Here I'm presenting you the CO2 production and removal efficiency, the result that we obtained in terms of CO2 production and removal efficiency, because as we know, when organic compounds are oxidized by bacteria, they release carbon dioxide. So we know that carbon dioxide is one of the greenhouse gases that is responsible for global warming. So we want to reduce these emissions. This is why also we use the algal photobioreactor as a second stage treatment. And as we see, we have the results in terms of average CO2 production for the first reactor in which there is the oxidation of organic compounds. And the average production of carbon dioxide was around 5 up to 16 grams per cubic meter per hour. And the CO2 capture efficiency ranged between 38 up to 95, 96 more or less percent. Also, as we see here, there is a gradually increase in the CO2 production, because as we can see in the previous slide, there is also, we gradually increased the inlet load of toluene, and there was more oxidized compounds, so more CO2 was produced. Here, there are the results in terms of total suspended solids and biomass production during the overall time of the experiment. As we see, we reach in the moving bed bioreactors up to 4.1 gram per liter, and in the algal photobioreactor we reach up to 3.88 gram per liter. So there was quite a lot of biomass. And here I'm showing you the chlorophyll A. Why we measured the chlorophyll A? Because we want to monitor the stress of microalgae in the second algal photobioreactors. So as we see in this slide, the algae, the Chlorella vulgaris, were in a, let's say, in a good shape. So there were not abiotic or biotic stress factors. In conclusion, I want to say that we obtain a solvent removal efficiency up to 99% under the investigated condition. The algal photobioreactor was able to reach a CO2 capture efficiency up to 96%. The algal photobioreactor also reached the biomass concentration of 4 grams per liter, with a biomass production up to 2 grams per day. And as we seen, the use of alternative source of nutrients, that we use urban wastewater and direct wastewater, allowed to reduce the use of chemicals, besides promoting the production of all other products such as lipids. In fact, now we are doing the extraction of lipids from the biomass that we collect during each stage, to evaluate the possibility to produce biodiesel from this biomass, so to make the system more sustainable. And also, next, we want to test these reactors with a mixture of contaminants and also with hydrogen sulfide. So, thank you for your attention.
Okay, we have time for a couple of questions before moving. I knew Bart was going to ask.
Thank you for your very nice presentation.
Thank you.
One question, maybe I missed it, but the pH in your algae reactor, is that controlled? What was the pH? Did you specifically add alkalinity?
Yeah, I didn't put the results also. We have the results in terms of dissolved oxygen, how we change the pH, the temperature. But yeah, the pH, it was not controlled. Like we try to we have the results, and the pH was more or less, let's say, stable between 6 and 8 into the algal photobioreactor. So we didn't obtain a really high alkalinity, fortunately. So it was more or less, yeah, in the range 6, 8, 8.5 more or less. This was the range.
Vincenzo, what was the gas residence time in the photobioreactor? Because I recall...
Yeah, the pressure.
The gas residence time. You have 26 liters of photobioreactor, right?
26
liters, and you're injecting 1 liter per minute.
The
airflow
flow.
rate.
The flow, yeah. It was 1 liter. And then we decrease a bit, because we increase a bit the toluene concentration, then we decrease a bit the gas flow rate at 0.5. And then during the last stage, we increase again at 1. It was a matter of trying to maintain stable,
the load.
As much as possible, the toluene concentration. So we play a bit also on the airflow, the inlet a bit.
Okay.
Thank you.